Okay, so we are our last section, right? Man, time goes so fast when you're having fun. Our last section of Gen Chem 1, and then we'll have an exam on this last section, and then the final exam. The final exam is comprehensive, right? So it'll be questions off of the hourly exams, and I talked to the other instructor, and we're going to replace your lowest exam score with your final exam score, if you do obviously better, right? So it's an opportunity in case something happened, like you got sick or whatever. That's kind of what the objective is there, but also to help you out. Okay, so we're still talking about quantum chemistry and trying to explain why, like, at the very small, as things get smaller, the science gets very odd, and you can't really, it's very hard to relate to it, because it's like saying, I think we talked a little bit about it before, it's almost like saying, okay, here's a piece of chalk. Well, it can't be in that position. It can only be in this position, and over here. Things that we can't even relate to. It doesn't even make any sense. And one of the guys who was instrumental in developing in quantum mechanics, I mean, it has yet to be proven wrong. But yet, why doesn't it work for baseballs flying across a baseball field? Again, so there's something's wrong somewhere, right? But, and like this guy says, if you don't understand quantum mechanics, well then, right, if it doesn't shock you, then you haven't really quite got it grasped it yet. I don't know if anyone's grasped it. So we are just talking about some of the fundamental outcomes of this to try to give you some idea as to where the science is at, and to, otherwise we can't explain simple things around us like colors of t-shirts. Atomic orbital energy. So we're just talking about atoms. And remember, there's only one equation that could be mathematically solved with all these Schrödinger equations and things that we haven't talked about for more advanced chemistry classes. But that one atom that we know all the answers to, that we know all of its energy levels, that we can explain and apply all these solutions to, in quantum mechanics, is which atom? Hydrogen. And why was that? Do you remember? It had the least number of electrons, only has one. So that's, you think with supercomputers we could do a lot better nowadays, but okay. So that's where all this is coming from. These are all answers to the hydrogen atoms. This is really hydrogen atom, but we're applying it to everything, all the atoms, because, well, it's kind of like the ideal gas law. It gave us rough answers, and it was good enough. And maybe not exact, but it's rough answers. So an electron configuration consists of placing all the electrons an atom has in atomic orbitals from lowest to highest energy. So these orbitals, these are the energy levels that these electrons can take. And the number of electrons that fit in any particular orbital, Dylan, is what? How many electrons can I put in each little orbital? A little bit higher than one. 2. You can actually put 2 in. Okay. And we're going to start playing with this. It's kind of like an orbital is just a line, and then we can put 2 in, so the first one goes up, the second one, if you draw the first one up, the second one has to go down. I don't know if you've ever done this before, but that's the game we're going to be playing. Okay? So how do we know the order in which to fill these orbitals? So we're supposed to write what the orbital is down here. Right? Like 1s or 2s or 2p, whatever, we're supposed to write down what the orbital is. And, well, I see us having 2 options. One is if you have a photographic memory, just memorize this, right? And start at the bottom, right? Because energy goes up. So just start at the bottom. You fill this one first. What's next? You fill that one. Well, I can start filling it in, actually. All right, fill up this one, then fill up this one, then fill up 2p, so there's 3 lines, and then we go across, right? And then you keep going, all right? I don't know if you could see what I was doing. For 2p, there's actually 3, so you're supposed to go like this first, and we'll talk about why as you keep going, okay? And we'll talk about why, but Ah, come on, memorize that thing? That's not going to be too fun. I think it's much more efficient to use the periodic table to figure out what these electron configurations are. And again, what is an electron configuration? For example, if this was where I stopped, how many electrons do I have there? 2, 4. I don't know if you can see. I have 10 total, right? I have 10 arrows, so I have 10 electrons. So that means I'm really talking about who has 10 electrons. Emily, who has 10 electrons? What element? What has 10 electrons? Neon. So this is how neon would look, but what is this electron configuration? You have to write it out. So, and we'll do this. Whoop. 1s, 2s, 2p. All right. So how do you know how to do all this? It's a lot easier. This is looking really complicated and ugly. Let's just follow the periodic table and then solve these problems, right, like writing electron configurations. I think it'll be much easier to see what to do. So the periodic table really tells you the order to fill stuff up. And if you notice on all these, remember for S, that meant that L was 0. So there's only one box, because M sub L only has one number. Remember for P's, that's where L was 1. So then M sub L could have 3 numbers, -1, 0, 1. So for P's, there's going to be 3 boxes for P's. For S orbitals, there's only going to be 1 box. For D's, that's where little l was, what number, Lauren? 2. So that means my M sub L will be -2 all the way up to +2. That's 5 boxes, 5 orbitals. 1, 2, 3, 4, 5. Okay. So if you recognize a periodic table, man, it's really set up that way. Look at that. Here's 2 boxes right here on this whole side. Group A, right? What do we call these? The alkaline earths and the alkalines? That's where we're filling up the S's. And all you do is just number them from top to bottom. 1, 2, 3, 4, right? So, because there's two we're filling in. The hint over here, right? All these nonmetals, right? Groups, what do we call those? Groups 3A through the nobles. If you count, there's actually, where's my little pointer? How many atoms are going over here? 1, 2, 3, 4, 5, 6. So 6 all the way down here for each period. That's the P's. So you're filling up the P's here.
So
Yeah.
we're missing a few boxes. 3.
We'll get the point. The point is we'll get the point across, though. All right. So I didn't make a perfect periodic table, but the point is there is no such thing as a 1p. It starts with 2p, right? So 2, 3, 4, 5. Okay. And what the heck? What happened there? It happened once before. There it is. Okay. Hopefully we didn't lose it. We didn't? Okay. Notice we got S's have 1 box. And how many electrons go in an orbital? 2. So that means you're wrapping up the 1s over here. You see that? So hydrogen is 1s, and helium, its electrons also going in 1s. And then the D, we said there's 5 possible M sub L's, so there's 5 orbitals. Well, that's how many electrons then? 10, because 2 electrons can go in each orbital, so that's 10. Well, if you count across on these transition metals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 going all the way across. So these are here you're filling up the D's. It starts at 3. Okay. And then here's our F's. I don't think, you may never get this far. I'm not sure you'll ever get that far. Okay. So let's just use the periodic table to write some of these. Now, when they say writing electron configurations, again, the idea is 1s2, 2s2, 2p3, those kinds of answers. And there's two ways to represent those answers, those electron configurations. One is an orbital diagram. The other one is the electron configuration. It's two ways of giving the same answer. And we're just going to cover them both. So let's start with this orbital diagram for nitrogen. And orbital diagram just means draw the orbitals. Okay? But let's list them out first. And the trick, I think, Lorena, is figuring out how many electrons does nitrogen have? Nitrogen has 7. Okay, so nitrogen is pretty much over there. Nitrogen is somewhere right in here, right? That's where we're going to stop. So we start by filling in 1s, right? And how many orbitals do we draw for 1s again, Kenneth? 1, okay. And how many electrons go in an orbital again, Megan? 2, okay. So we've got 2 done. But Giselle, how many electrons do we have to use up? We're talking about nitrogen, so we have to keep going to 7. We only got 2, so we got to keep going. So Sydney, we filled up. This is what I like to do. I like to just follow it on the periodic table. There's 1s1, 1s2, so we filled it up. What's next? See the numbers? What's next is number 3. Now we're filling up the 2s. And how many electrons do I put in there, Sydney? 2, right? I guess you'd start there, but then you got to keep going, right? So it would be 1, and then you got to put in the second one. So following the order on the periodic table, Ashley, what orbital would we be filling in next? We filled in the 1s, the 2s. We're still not at nitrogen. Now you start filling the 2p. Okay. Now how many orbitals, Baudi, am I supposed to be drawing for a 2p? How many orbitals was I supposed to be drawing? The hint is you know this is 2p, this whole guy over here. So if you count, there's actually 6 before it's filled up. So 6 divided by 2 is 3. So that means there's got to be 3 orbitals. If you forget, right? Or p means little l is 1. So m sub l can be -1, 0, 1. There's your other way to figure it out. So there's 3 orbitals. Okay. So as we've been filling this in, we've been following these rules. We've been following this rule, the Pauli exclusion principle. You can't have 2 electrons that have the same set of quantum numbers, like both pointing up. That's the Pauli exclusion principle, is that when you put in that second arrow, it has to be the opposite of the first one. So if you draw this first arrow going down, the second one has to be going up. That's the Pauli exclusion rule. Okay, and it's just an outcome of quantum mechanics. So 2p, we drew 3 orbitals. We have how many more electrons to put in here, Rebecca? 3 more. All right. So Hund's rule is the rule on how you put in those 3. Okay, because there's a lot of ways to put in 3, wouldn't you think? Here's 1, there's 2, there's 3. Or you could do 1, 2, right? Oh, there's 3. But you're supposed to put them, Hund's rule says you put electrons all in the same direction because that is the lowest energy. And that's what this word meant, lowest energy. Ground statement, lowest energy. So if you're supposed to give them their lowest energy, Rebecca said put in 3 more, put them all pointing up or all pointing down. It doesn't matter. You're done. This is the orbital diagram, the ground state orbital diagram for nitrogen. Right? The ground state, same type of information, but they just want it represented differently. Electron configuration. So now what you do is you just pretty much forget the orbital diagram and just write 1s superscript number of electrons, 2s superscript number of electrons, 2p superscript number of electrons. So what would that look like, Alyssa? That would look like 1s. How many electrons in 1s? 2. So 1s2. Keep going. 2s2. 2p. How many? 3. Yeah, 2p can take 6, but that would be too many electrons. Because if you had 6 in there, you'd have 6 and 2 is 8. That'd be 10. That would be the answer for neon. But they said nitrogen, so we stop here. Okay. So when they say electron configuration, don't be drawing orbitals with N arrows. If they say orbital diagram, then you got to start drawing orbitals and diagrams. You can draw boxes if you'd like. You know, sometimes a book prefers this. It doesn't really matter, right? But you got to have those arrows in there. And I don't think the book hit on this enough. The lowest, if they did not say ground state, you write any electron configuration you want, I can't mark it wrong, as long as you had 7 electrons. Because there's nothing wrong with this. What's after 2? Here, let's give you an example. Manual, what is the next orbital higher in energy after 2p? All right? Because you're wrapping around here, you're filling 1s, 2s, here's 2p, then you're filling 3s. So 3s is next. So we could have wrote 3s, 0. And keep going. All right, 3s, 0, 3p, 0. Nothing's hurting. It doesn't hurt anything. And what I could have done, if it did not say ground state, I could have kind of played a game here. Let's erase one of these guys, and let's put them in here. I can't mark it wrong. It's just that it's not the ground state. It's not the lowest energy. You have 7 electrons. Yeah. So this is where the spectroscopy is coming in. He's jumping from this orbital in a higher energy back down to its ground state. It's emitting one of those little colors that we saw when we were looking at nitrogen through that tube, spectroscopy tube. Okay? But let's get it back to how it was. Okay, so that's some of the game we're playing. So you do this. Write the ground state electron configuration for arsenic. Write the ground state electron configuration for arsenic. Okay. And arsenic is number 33, so you got a lot of electrons. Now remember, this is not the orbital diagram. This is just the electron configuration way. Go all the way to 33. Stop when you hit 33. Yes, Lauren. Okay, so what you're going to do is you're going to start here, say 1s. I almost say it verbally before I write it down. I'm going to have 1s, 1s1, 1s2, 2s2, 2p6, 3s2, 3p6. See what I'm doing? And then you just keep going and keep filling it up, but I stop when I hit this guy.
So when you get, so when you're going to have
4s2, and now I'm filling up this guy. This will be what? 3D with a superscript. If you're not sure, you can just count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So you could put the 10.
Yeah, you have to write 10.
It's not too big, like how you told us, like on this side you gotta divide by.
Well, D means that there's actually 5 orbitals. So that means it can hold 10 electrons. That's the maximum. So it's maxed out. Because we got to keep going. Arsenic's 33.
Okay,
Zinc, you'd stop at D10.
Okay, so then we write B10 and then we put.
And now you have to write 2p, 3p. Now it's 4p.
And then we just write 4P3.
4p3.
Okay.
All right. So follow the periodic table, fill it in. Steph, do you have an answer for me? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now if she stopped right here, let's say she stopped right here. This would be the answer for what element? Zinc, exactly. That'd be the answer for zinc. But she kept going, and she said 4p3. I can never remember this stuff. Okay, this is 2p, 3p, 4p, 4p1, 4p2, 4p3. I agree with her. Everybody agree? Okay. That's a lot to write. So someone came up with a shorthand notation, right? The noble gas core notation. Noble gas core notation, just a shorthand way to write the electron configuration. So the next problem is, okay, let's write the electron configuration, exact same answer, but use noble gas core notation. So all you do is what? Does anybody know? Exactly. You start at argon. So the only way I can do without screwing this up is I look at the element on the periodic table I'm interested in, and then I go back. Don't go forward because that's going to screw you up. You don't have enough electrons to go forward. You have to go back. All right, until you hit a noble gas, argon, and that's where you start. Now the trick is you got to put argon in what? You got to write argon, and then they want to see argon in brackets, and then you start. Do the exact same thing again. So you'd start with, what is this? 4s. Start with 4s, and then you play the same game. In other words, you just finished off this whole part right here, all the way up to 3p6. So you don't have to write all that. All right? So you can kind of just drop all this and make that argon for this answer. It's a lot quicker. So you'd have 4s2, fill in the D's here, fill in those at P, and you got it. So hopefully that's all you wrote. 4s2, 3d10, 4p3. Okay. So for something that's supposed to be so complicated, it really isn't so bad so far, right? Okay, so that's noble gas core notation. Valence electron configuration. It says that the valence electron configuration of an atom consists of the electron configuration outside of the noble gas core, or the pseudo-noble gas core. So write the valence electron configuration for arsenic. Now what they're driving at here is this is a really big deal. And we're just writing electron configurations. I don't think we can really appreciate it in general chemistry. But if you look at this electron configuration, where are the highest energy electrons, right, Dylan? Because there's all these electrons are supposed to be at different energies. Where are the highest energy electrons? Yeah, the ones that are farthest away, way out there at the 4p3. So every single chemical reaction, every single chemical property, everything that determines the chemistry of this element is way out here, the outermost electrons. Because these guys are just, they don't do anything. They just sit there. They're way blocked in. Everything, they're too stable. They're way inside. These very high energy ones, the highest energy ones, are the furthest out. They're going to do all the chemistry. That's why they're really only concerned with valence electrons. That's just another word for valence electrons. Okay, so the trick really is how do you pick these out? Well, this is really it. Outside of the noble gas core electron configuration, or pseudo noble gas core electron configuration. So we're supposed to look at arsenic. So what is outside of the noble gas core? Well, it'd be this whole mess, 4s2, 3d10, 4p3. So you'd like to write that as an answer. That's way too many electrons, though. All right? I mean, you'd like to write this as your answer. 4s2, 3d10, 4p3. Okay, that's what's outside of our noble gas core. What does this mean? Pseudo noble gas core. Does anybody know? What is a big chunk of orbitals and it's completely filled? You have 5 of them. 10 electrons total. D10. D10 is not a noble gas core. It's not a noble. All right. These noble gases, they don't react. They're extremely stable. That's why they're always picking the electron configurations outside of them. Well, likewise with the D10, you fill up D10, it's extremely stable. So it's not a noble gas core. It's just a D10. So they call it a pseudo noble gas core. So you're not supposed to look at those. So there's my answer. It's just, how many valence electrons, Emily, would you say arsenic has? Two and? Yeah, 5. Atom. Right? So, because the answer is 4s2, 4p3. It really has 5. And if you look up here on the periodic table, here's your answers up here. It's really kind of a trick question. Because look, here's your answers up here. These group numbers are the number of valence electrons. If you have something over here in group 1, and you write the electron configuration, you better have only 1 electron total. Group 2, you better have 2 electrons total. Arsenic, according to this, is in group what? 5, Roman numeral 5. So you better have your answer. It better have 5 electrons. And it does. So you can do that as a little check when you write these valence electrons. Add them up and make sure it matches the group number in the periodic table. Otherwise, you screwed up. All righty. So let's go to the boards. You can talk about this stuff, make notes if you'd like, and then we'll wrap it up. So just write your answer on the board. Make sure it agrees with the folks around you. And the quicker you get up, the quicker you can go and have start your weekend. Right, Connor? Jeez.
Yep.
Get moving. Yep.
Did I by chance use my calculator here a couple days ago?
I don't know. You need one?
Well, I mean,
I can
don't
grab
need
another
now,
one.
But I don't know where I left mine.
I can grab another one. Don't worry. It'll pop up somewhere. So which of the following orbital diagrams are not allowed due to the Pauli exclusion principle? So just remember, the Pauli exclusion principle was the one where 2 electrons couldn't have the same set of quantum numbers. That's your hint. So you've got A, B, C, D. There's 4 possibilities there. Just write your answer on the board and see if the folks around you agree. Now, which of the following orbital diagrams are not allowed? So there's something wrong with some of these. See if you can recognize it. Okay.
Okay, so why do you have the
Yeah, okay. Remember there's 2 rules. If you forgot, we went over it pretty quick. There were 2 rules. They called it Pauli and Hund. Hund was the one where if you have a bunch of boxes, a bunch of orbitals, you have to put them all in the same direction, right? That was Hund. Pauli was the one where, okay, if you have an orbital, a bunch of them, you just can't do what? If this one's up, the next one has to go, that's Pauli. If you want to break Pauli's rule, you do this. Can't happen. So just look at that question, identify which configurations broke Pauli's rule. It would be what? A, good. A, and is there another one? Yeah, C. Oh, yeah, good, good. I didn't see that. C. Right?
And D, right?
Oh, D is breaking whose rule? So it's kind of a trick question. This one's breaking Hun's rule. But it only breaks for, it's only asking for Pauli, so don't circle D.
But both of the arrows on 2B are going down. It's up and down, down.
Yeah, so for D, D is breaking Hun's rule. In B, they're both going up. Remember, these are different orbitals. It's just that Pauli is, they have to be in the same orbital. So if I erase this and put it here, that's breaking Pauli. But they're in different orbitals, so it's okay.
So you don't have to put the whole orbital to do another one?
Yeah, it has to be the same orbital. Right? So C, these two guys, see how
Oh, you can only have two in them.
well, not only can you only have two in them, but the point is you've got two with the same direction, same set of quantum numbers. Can you see that? The same orbital, and they're both going the same direction.
So where should this third one be?
Oh, you can't have three. All right? So, yeah, you can only have two. And that's another reason for Pauli. You can only have two in there.
With EX2s, are just talking about in general or ground state?
Okay. So does EX1 make sense then to everybody? We're good to go on? Megan? Make sense? Okay. Try EX2.
There's a D in there.
Circle the following electron configurations that are possible. So only circle the ones that are possible.
Just in general or ground state?
Yeah, so they're not talking about ground state. They're talking about just possible. It's possible. They're not breaking anybody's rules. And I added a D, so yeah, maybe you don't have a D. So I added a D. So circle. So write down what you think on the board, your answers for the ones that are possible. Okay. You guys write down your answer, then we can go on.
What if for D, the 4S1 can jump into the 2P?
Yeah, they're possible. So that you can have it promoted. That's just not ground state is all.
Okay, so it is possible.
Yeah, it's possible. It's just not ground state.
Okay, so okay.
So did you circle? I think everyone does. Everyone have? Is A possible? No, don't circle it. Is B possible? Yeah, there's nothing wrong with B, right? S's can have 2s, up to 2 electrons. P's can have up to 6.
But you don't have to fill in the whole state before you move on to the next S, right?
So this one, what's wrong with this one? This B is not the what state?
Ground state.
It's not the ground state. So that's okay, right? Circle that are possible. So it's just, the technical word is excited state. So when you jump from an excited state to the ground state, that's where you could emit a little bit of light, like red or something. Okay. Is C possible? I don't see anything wrong with C. Is D possible? Yeah. Nothing wrong with it. Okay. Give the electron configuration of the ground state of iodine, both with and without noble gas core. Keep going, Megan. No one ever said life was easy. Now, I could have asked for orbital diagram. That would have been worse. 53 little arrows. So this one isn't bad. Oh, and they like them, Lauren, they like it to go in a vertical line. Sorry, horizontal line.
Okay. Fine.
And then you got to fill them. 1S, 2, 2. Oh, okay, that's fine. That's fine. Does anybody have a question on how to do this? Kenneth.
Why is number 43 whited out?
43. There must be a question on it. Yeah, why is that? Maybe they're not so sure about it for some reason. It could be its name. It's a good question. Because see, starting at 93, they're whited out. 104 is whited out. Good question. So they want the answer both with and without noble gas core notation. So did you end up with, for the noble gas core notation, krypton, 5s2, 4d10, 5p5? Okay. I'm too lazy to do the other one. Okay, EX4. Zirconium is a group 4b element in period 5. So remember, period is rows, groups are columns. What would you, in the periodic table, what would you expect for the valence shell configuration of zirconium? So they want you to write the valence shell electron configuration for zirconium. So that's ZR. Zirconium is number 40, if you haven't found it. So I think that the easiest way for me to do this is to write the noble gas core notation. And then I kind of just erase stuff. That's how I do it. I kind of write the noble gas core notation, and then I erase my noble gas cores, erase any pseudo-noble gas cores.
When you write this, after you get to where it's saying I don't know why I said
What do you? What's the superscript here?
Oh, sorry. Hold on. Okay, read it. I was lost. Where do you go from there? Do you just leave it like that?
Well, they want valence, so what do you have to erase? You don't include what?
The one that's full. Like the,
Right. So does anyone have an answer? I hear 5s2, 4d2.
Yes.
Anybody else come up with that? Does the answer make sense? How many valence electrons? 4. And they say it's in group 4b. I should have those numbered. Well, they're kind of numbered up there in red, but I should have those numbered. So that matches. Okay. What would you expect for the configuration of the outer electrons of manganese? What are they asking for? The valence. They just kind of changed the word on you. So write the valence electron configuration for manganese. Where the heck is manganese? Manganese is number 25. Atomic number 25. So what's the answer for EX5? 4s2. 3d5. Okay. We're almost done. Okay, so this big paragraph, what it's saying is that we're going to write ground state, we're going to write ground states. And there's a little bit of a trick to it. In other words, when you can get D10 or D5, you move electrons to get it. Okay? So what does that mean? Go ahead and write the electron configuration for copper, right? The noble gas core electron configuration for copper, right? Don't move anything around. In other words, just go ahead and write the regular noble gas core notation for copper. And then I'll show you what they're trying to say. Go ahead and write the noble gas core notation for copper, just as you normally would. The noble gas core notation for copper. So Audrey, what did you write? What did you write in brackets? AR. AR, okay. And then Paul, can you finish it? AR, and then what? AR, then 4s, 2, 3d, all the way up to 9. Okay. So this is wrong for a ground state. Because what happens in nature is that, remember, what were the super stable was the noble gas core and also pseudo. And pseudo noble gas core is what? D10. And this D5 is also really stable. So what you have to do is you have to, now you can't just erase the 9 and make it 10. You have to, because you can only work with copper's electrons. And copper only has, what, 29 to work with. So you can't just pop an electron. You have to make the 2 a what? A 1, and then you make D10. That's how you do this. That is the ground state for copper. And that's what they're saying. When you can make D10 or D5 really easily, you do that. So following that trick, write the noble gas core ground state electron configuration for vanadium. Vanadium is atomic number 23. Right, the noble gas core ground state electron configuration for vanadium.
Where do we
Yeah, good question.
I don't know. Do we just cross this out, or do we go back?
What do you got to do?
Trying to make it.
All right. So, okay, so vanadium. What's a noble gas core? Argon. And then what did you have? 4s0. Exactly. That's the trick. So make D5 and D10 when you can for ground state. So be careful on the homework. Okay. Okay. So I think that's good enough, right? I think you got the idea, right? So have a good weekend.